So for our presentation, we will be talking about the effects of microplastics on bivalves. My name is Gemma.
I'm Lee.
I'm Jessica.
And I'm Anne-Marie. So plastics have been accumulating in our oceans for quite a while since we started producing plastics. According to the NRDC, 8.4 million tons of plastics are being put into our ocean annually, which is somewhere between 15 and 40% of plastics we manufacture. In this map, you can see the coast of Maine, and in comparison, the red dots have 50 to 100,000 pieces of plastic per kilometer.
So one type of the plastics that are being accumulated in these plastic piles are microplastics. And microplastics are minuscule particles that are under 5 millimeters in size. And there are two different types of microplastics. The first type are manufactured microbeads. So these are already pre-made to be in their smallest form and can be found in things such as toothpaste and face washes. And the second type of microplastics are those plastics that break up into their smallest form, because when plastic litters into the ocean, it doesn't just disintegrate, it becomes microplastics and remains there. With the abundance of microplastics out in the ocean, many marine ecosystems are being affected by this. Some of these marine ecosystems include salt marshes, the open ocean, and the intertidal zone. And some of the organisms amongst these marine ecosystems being impacted are the sea turtles and the seabirds. So since Maine contains all of these marine ecosystems, if microplastics are indeed affecting them, then Maine will be prone to these.
So some of these organisms being affected by this abundance of microplastics are bivalves. Bivalves are mollusks that live in shells. They are filter feeders, so that means that they siphon in water, and they take this water and they take the oxygen out of it to breathe, and they take the phytoplankton out of it to consume. They're really important to a lot of ecosystems. They're widely consumed by a lot of birds and other animals, and they're consumed by humans, so that makes them economically important as well.
First off, where do these plastics come from? Microbeads in face wash and toothpaste often make their way into the ocean through the drainage system and pipes that lead out into the open ocean. Other sources for larger plastics come from urbanized areas along the coast and litter along the beaches. These plastics are often swept up and deposited into the ocean, where they are broken down into microplastics. Now, as we know, bivalves are filter feeders, so they use their siphons to take in water and filter through oxygen and food, such as phytoplankton and detritus, naturally produce microparticles. And the issue with this is that since they're so similar in size with the microplastics, bivalves often mistaken them for their natural food. So when they take them in, it can cause potential harm to the bivalves.
Our research question was, how do microplastics affect the shell thickness, filtering system, and buoyant weight of Mercenaria mercenaria, Crassostraea virginica, and Vidalis edulis, which are the hard-shell clam, the oyster, and the blue mussel?
The hypothesis that we came up with states that if microplastics are added to a controlled environment with bivalves, the bivalves' health and wellness will be affected by having weaker shells and failing filtration systems.
Some of the goals we came up with for our research project was to see how commonly used plastics, such as those in face washes or that come from your laundry, affect commercially important shellfish that people eat all around the world. So we researched the impact they had on the organisms, and we considered the potential impact it could have on humans and the impact humans have on them as producers of plastic.
So, as Anne-Marie just stated, we wanted to use microplastics that are commonly used in everyday life and commercially important. Therefore, we decided to use 3 different types of microplastics. The first type are microplastics found in face wash, such as the Olay Fresh Flex. The second type of microplastics we decided to use are pre-made microbeads that can be used for nail art. And the third type of microplastics we wanted to use were lint, because when washing fleece clothing made with 100% polyester, then microplastics are captured in the lint, and when the lint is littered, it can then get into the ocean and cause further damage.
So the bivalves we tested, we gathered at a site called Recompense in Freeport, Maine, and we gathered 6 samples each of 3 different species, these species being Mytilus edulis, or the blue mussel, Mercenaria mercenaria, or the hard-shelled clam, and Crassostrea rigidica, or the oyster. So this is what our setup looked like. We had a large yellow tank that was filled with fresh water. This fresh water was being filtered through a filtering system and into a water chiller. The water chiller was set to 9.4 degrees Celsius, which was the temperature that we measured when we collected our organisms at Recompense. We had 6 tanks. 2 of the tanks contained 1 species, and in each tank we had 3 organisms, the control group being in the front and the microplastics group being in the back.
So over the course of our 6-day experiment, we had to measure and weigh our bivalves daily. My job was to measure the shell length of the bivalves, which was important because we wanted to observe whether or not microplastics had a direct impact on whether or not the shells themselves grew. So this would be done using a caliper, which measures in millimeters, and we would have our bivalve, and we would take our caliper and clamp it down on the shell, and we would measure what the length was, which would then be recorded in our spreadsheet.
We also measured their buoyant weight, which is the weight they are when they're suspended in water. It's only the weight of their shell, because when they're suspended in water, their bodies are neutrally buoyant, which means that they weigh virtually nothing. The way this worked was we had a scale, which measured in grams, and we had a knitting needle across the top, to which we tied a string, and then at the bottom of the string, we had an organism and suspended them in water.
And I was in charge of feeding the bivalves daily. So all of the bivalves in each tank were fed a 10 milliliter combination of healthy green algae and phytoplankton culture. However, the experimental bivalves, which were exposed to microplastics, received additional 3 milliliters of the microplastics found in the Olay face wash, and 9 beads from the nail art, and 1 squared centimeter of the lint.
I was in charge of writing down all of this data and recording it in a spreadsheet. And once we were done collecting all of our data, we performed a collective dissection where we shoved all of the organisms, even the organisms in the control group, and we took a look to see what physical differences we could see on the inside just with our eyes, and then we looked at them under a microscope. And we cut them up a little bit so that we could see if there were microplastics in them.
As it is shown in this graph, you can see that there's an inconsistent change in buoyant weight. So the x-axis represents the change over time, and the y-axis represents the average change in buoyant weight for each species. The lightly colored bars represent the experimental bivalves, which were exposed to microplastics, and the darker colored bars represent the controlled environment, which were just kept in the controlled bivalves were just kept in a controlled environment. So as seen, there is no consistent increase or decrease between either the experimental or the control groups. And this graph now shows it has the same variables, except now the x-axis represents the average change in measurable width. So as you can see from the graph, for most of the days the shells did not grow. However, they only grew between days 1 and 2, and between days 4 and 5, we saw one of the bivalves decrease in size.
This pie chart shows the microplastics we found in each organism. So each wedge represents one type of plastic in one type of organism. There are no wedges for the nail art plastics because none of the organisms consumed any of them. So as you can see in the orange ones, the oysters consumed 5 pieces of face wash and 2 pieces of lint. Lint refers to either a lint strand or a lint clump. The hard-shelled clams consumed 4 pieces of face wash and 1 piece of lint. And the blue mussels consumed 3 pieces of lint and 4 pieces of face wash.
So here you can see what it looked like to see these microplastics within the bivalves under a microscope. Here you can see the strands of lint, the clumps of lint, and the balls of beads from the Olay face wash. And here there's a group, and here's a single one.
By the end of our experiment, we observed that there was no major change to the outer appearance of the bivalves, both in the control group and the experimental group. Their shells didn't show any major change. However, we did notice during the dissection phase that organisms in the experimental group, such as the blue mussels, were much easier to open as compared to those in the control group. And they also had drier bodies, which may which may suggest that the microplastics were having a negative effect on the filtration system of the bivalves. We also noted that the oysters in the experimental group had a much grayer pallor in comparison to those in the control group, which had nice, healthy pink bodies. And here we have a picture of the experimental oyster, and on the right, the control oyster.
So as for negative effects that we found that microplastic absorption, from what we could see, exhibits no impact in shell growth.
The bivalves were consuming microplastics, however, and this could have a potential impact on their metabolism because microplastics won't deteriorate within their systems like phytoplankton will. So they will feel like they're full when in reality they're not eating anything, which could result in death.
And the reason why this is important for us humans is because since these bivalves are eaten as a delicacy, if microplastics do indeed affect their metabolism, then it could either eventually affect our health or it affect us economically because many rely on selling these for profit. However, for future studies, we did want to change the bivalves that we are using. So next semester, if they continue this experiment, then it would be beneficial to use different types of bivalves that filter at a quicker rate because since we are just given a week for data collection and the oysters and the hardshell clams don't filter at a quick rate, then if we used bivalves that are still commercially important but different from those, then maybe the effects of microplastics in them will be a lot more accurate.
So we would like to thank Dr. Carrie Whitaker for providing us with wisdom and guidance on how to take on this project.
We'd also like to thank Maddie Halloran for providing support and constructive criticism.
We would like to thank Kate Kairos and Jenny Caffrey for showing us the importance of giving and receiving feedback.
And last but definitely not least, we'd like to thank our bivalves for being cooperative with us. The 18 bivalves names are shown in this. Emotional attachment to them, it was hard.
So are there any questions?
Yes.
So typically, how quickly do they grow? Like in a week's period, what were you expecting if they were consuming microplastics for them to grow? I guess I'm asking because I always thought they were slow growing.
We actually don't know. However, with our control group in comparison, it seemed as though they were growing at a similar rate.
Which was about how much?
Inconsistently.
So typically you can pick up a change in their growth using the Buoyant Weight method, much more higher resolution than using the caliper. Questions? Other questions?
Did you get to eat your subjects?
They were exposed to plastics.
Oh.
Do you have any recommendations for products that people might avoid using
Face
to
wash.
help?
With microbeads.
Yeah, just check your products and see if they have microbeads. They'll probably say like exfoliating beads for face wash, like exploding beads, some of them say. Stuff like that probably have plastic in them and you shouldn't use them. Some toothpaste, the ones that look like they have like little sparkly dots in them, those are plastics, so don't use those.
In addition, microplastics in face wash has been illegalized by now, to a point where it should be out of the general system by 2020.
The production of them in the United States is, you can still get them, so just don't get them.
How do you suggest we convince the general public of these issues, which general public can't actually see it? I mean, we were told that these jackets made from recycled bottles were such a great thing, that we're recycling, and actually they're causing more problems in the world.
Maybe just with general awareness, and this can include many advertisements that kind of say not to use them because of the harm that they are causing to our environment.
Also, in the picture on the first slide, the dark blue had the least amount of plastics, and it was still 0 to 2,500 pieces of plastic per kilometer, which is a lot.
Is there any sense that concentration of plastic was because I'm ignorant, so I don't know. Is it because it's closer to the equator, the water might be warmer, or current? Why? If there was if there would be a particular reason why it would be so concentrated off the southeast coast, and not maybe sort of further down into the Caribbean or what have you?
Well, the way plastics move around in the ocean are through gyres, which are a type of current. They're kind of like spirally things in the ocean that are like with the waves. So the dark red dots are some gyres. There's also the Great Atlantic and the Great Pacific trash heaps, which I'm sure some of you have heard of. And that's where all the plastics are accumulating together, which is probably that very large red dot. And also plastics are sinking down to the bottom of the ocean, which there isn't really a lot of information about what harm that's doing, but it's happening.
And additionally, since microplastics are so small in size, then they usually are overseen, and it's harder to get rid of them.
Frequently as well, a lot of microplastics are so small that they can go through semi-permeable membranes on really small organisms, and in that way they can also move up the food chain to larger organisms.
Yes.
So water treatment systems and things are not catching these things.
They're definitely not catching all of them. There's also a type of plastic that's broken up very small called nanoplastics, which they're definitely not catching. And these plastics are so small that they can actually permeate cell membranes, so like go through your skin. So they're definitely not catching those, and they're not 100% effective. So.
And last question. Have there been studies showing the amount of microplastics in the human body?
Not that we researched.
All right. Well, let's give this